Hi everyone, it's Mrs. H. Today we're talking about section 11.7, which is all about ratios of areas. We have actually seen a number of these questions already as we've been going through this chapter, but we're going to kind of formalize some things that we know here and figure out why those are true. So we're going to start out with this picture. We have two different triangles here. We have triangle A in orange and triangle B in green. And I want to compare the ratios of these two areas. Well, first of all, no matter which triangle I'm on, the first thing I'm going to do is I'm going to drop down my height. I always want to know my height of my triangle. And both of those heights are the same in this picture. Here's my height. It is that perpendicular drop down from the altitude, and I'll just call it H. Now, if I'm finding my two areas, I could write down my formulas for them. The area of my orange triangle is going to be 1/2 times my base, which is A, times my height, which is H. And then for my green triangle, I'm going to again do 1/2, but this time my base is B, but my height is still H. If I want to compare these in a ratio, I am going to just divide my two area formulas here. The 1/2s cancel out, the H's cancel out. What is the ratio of the area? The ratio is A to B. Well, we can formalize this and we can say if two triangles have equal heights, then we know that the ratio of their areas is exactly the ratio of their bases. And I could just skip all that work that I just did where I actually figured out what those two areas were. All right, similar picture. Let's take a look. I have two triangles here. My pink triangle has a height that I'll drop down like this, and I will call this height H. My blue triangle has a different height that I'll drop down here, and I'll call that one K. But note on both of these, what is the base? The base is the same, so let's just call that B. For my pink triangle, the area is going to be 1/2 times my base times my height. For my blue triangle, my area is going to be 1/2 times my base times my height. And then if I'm going to compare these two in a ratio, I'll just put them in a fraction. Cancel, cancel, just like before. Different things canceled, but I can still find the ratio, and the ratio here is going to be H to K. Well, again, I can formalize this and I can say if two triangles have equal bases, then I know that the ratio of their areas is equal to the ratio of their heights. And I could avoid that work that we just did. All right, one last example that we're going to look at where we're going to compare our areas. This last example is what if we have similar triangles? Now, I didn't tell you a scale factor here, so why don't we have our scale factor here be, times 2. It might not be accurate here. I didn't measure. I didn't actually count what the 2 are. All right, now what I want to do is I labeled these just as if they were regular old triangles. But now that I know my scale factor, instead of B, I could write down, well, that's double E. And instead of H, what I could write down is that is double K. And now let's do our two areas. My area for my purple triangle is going to be 1/2 times the base, which I'll put 2E, times the height, which was 2K. For my red triangle, I'm going to have my area as 1/2 times my base times my height. When I compare these in a ratio, my 1/2 cancels, my E cancels, my K cancels. My ratio, I don't want nothing on the bottom, so I'll multiply my 2 times 2, I get 4. I'll multiply and leave my denominator as a 1 so that I can still say it as a ratio. What is the ratio of these two triangles? Well, it's 4 to 1. You could do an example like this with actual numbers as well, so that you didn't have to have your E's and K's. It would work if your red triangle was 1 and 1 and your purple was 2 and 2. You would still get this 4 to 1. All right, let's formalize this. When we have two triangles that are similar, the ratio of their areas is equal to the scale factor squared. Take a look at our last example that we just finished. What was my scale factor? My scale factor was times 2. What was the ratio of my areas? It was 2 times 2. And where did that come from? That came from 2 times 2 because each length that I was measuring got multiplied by 2. All right, we have one more theorem that we're going to write down that is going to kind of put this all for any shape. But before we do that, let's actually do one more example. And our last example is going to be this problem right here. We have, oh, I need some lengths, don't I? Why don't we have that this side is 2 and that this side here is 3? And I want to find two things. I want to find the ratio of the areas and I want to find the ratio of the perimeters. Well, when I'm looking at these, I know that in this picture, whenever we have these parallel lines like this, I have to pull my two triangles apart. So I'm going to pull my two triangles apart here. I'm going to have my top triangle as my ABD. And when I have this one, I know my side length of 2. When I pull apart my bigger triangle, this is going to be a little bit off, but that's okay. This is going to be a CE, and I have to add those two sides together. So now it's 5. I know from previous chapters that these two are similar figures. And so what I can do is I can find my ratio of my areas and my perimeters. I don't know all of my side lengths, but that's okay. We can still find the ratio of the areas. Let's think about this. Here, my ratio of my areas is going to be my scale factor squared. So my scale factor, ABD, is 2 to 5, which means that the areas, I'm going to square my scale factor, so it's going to be 4 to 25. I could also find the ratio of the perimeters. I actually don't really like to think about perimeter or side length when I'm talking about this section. Instead, I just think about lengths. Lengths and areas. What am I talking about in each problem? Well, here are lengths. That doesn't matter what I add up. I'm going to have that same scale factor for all of the sides. It's always going to be 2 to 5. So when I add them up, it will just be 2 to 5 plus some multiple of 2 to 5 plus some other multiple of 2 to 5. And so it's going to actually stay as 2 to 5. There is one other thing that we can talk about in this picture, though, that's going to be really important. This area is 4 parts when this area is 25 parts. Back on my original picture, I could now compare the triangle to the trapezoid that's on the bottom. If this top area is 4 parts and the entire big triangle is 25 parts, then the trapezoid on the bottom here is 21 parts. We're going to see a lot of questions like that where you have to kind of break it up first and then go backwards. All right, and our last theorem here, our theorem 11.7. If we know the scale factor of two similar figures, well, first of all, the scale factor is telling me about my lengths. So any length that you measure is going to be in that same scale factor. When I measure perimeter, perimeter is just a length. So my ratio of my perimeters is still going to be A to B. You could talk about the ratio of one of the sides. I could compare right to right, or I could compare left to left, and that is still going to be that length scale factor of A to B. The ratio of the areas is going to be A squared to B squared, like we kind of just saw up above. We're going to see a lot of pictures involving these, including some tough trapezoids. So just kind of keep straight what you know when as you go throughout each of these pictures. And often you're going to want to break pictures up into pieces. So just keep that in mind as well. All right, good luck with everything. Hope this made sense. Of course, ask questions in class. Thanks, everyone.